So today is the final edition of the cursed year of 2020 of the Programmers Club. We will have today Abhishek Chougule. I hope I pronounced your name not too incorrectly. And he will be talking about FITS. You mentioned a friendly neighborhood of astronomers, which somehow implies that there is an unfriendly neighborhood of astronomers. But today we're just going to talk about the friendly one. So you may start whenever you like.
Sure, yes, I'm ready. Am I audible?
Yeah, we can hear you well.
Yeah, perfectly fine.
Thank you. Yeah, so today I'm going to talk about FITS file. Although the overall presentation is quite basic, but I think it would be helpful to have a recapitulation. I'll just go through the basic concepts more or less. So what are FITS files? What does it actually what does it stand for? So the acronym is Flexible Image Transport System. And as we proceed further along in the presentation, we'll realize that it's pretty much flexible, and it's not just for images, and you can transport even spectra and images and binary tables as well as ASCII. So why to use FITS and not any other image format? Well, other image formats, let's say like JPG, um, have losses, so they are not they are actually compressed. So for finer details, or to have to look into really fine details and faint details, um, we have to, I mean, those things get compromised. So FITS comes in there. It's raw and uncompressed. uh, Another advantage is that in the header, it contains information how the image was obtained and where it was obtained. Not only that, but also uh, many other things. What was the date of the production? What are the coordinate systems that are being used? So on and so forth. Although there are some disadvantages, like they are big files, and it needs to be manipulated to see things. Nonetheless, the benefit uh, is what we are looking for, and it outweighs these disadvantages. So, what is the basic structure of FITS file? So, if we look at a FITS file, we can visualize it as divided into chunks of data. Each chunk of data uh, is referred to as a header data unit, and there is the primary header data unit, which is the first one, and then you have the others, which are called the extension header data unit. Each of the header data unit, as shown in the figure, has a header and has a data. The header is ASCII, that means it has the details written in ASCII, and it gives us the information about the data. How long is the data? When was it obtained? For example, what were the observing conditions? And comments if there are any. Um, on the other hand, the data unit can be ASCII as well as binary, or it can also contain the pixel values. So an example I will show you for a header data unit is for the primary. So this is a FITS file which has one primary, of course, and then it has an extension, which is a table. The type is ASCII. Now, if we look at the primary, we have the header and the image. So the header gives us the information. I'm not sure if it's well enough visible to read the comments and the other things, but maybe in the later slides, I have a zoomed in version. So we can see that you can write in the comments, for example, who was the file originator, what was the date of the file when it was generated. And on the right, we see the data. It's basically an image. So let's look into the header data unit. So as I've mentioned, it describes the corresponding data unit, and it's in ASCII. Now, each of the entry is known as an image card, and it goes by the syntax of keyword followed by the value and a comment string. Well, comment string is optional, but it's always good to express our data well, so that that it's readable and others can understand. Each keyword can be at the most 8 characters long, but there are hierarch cards which can be more than 8 characters long. And when we are doing that in Python, because I work with Python, it gives us a warning saying that it's more than 8 characters. However, it does write those into the FITS file. Then the value can be an integer, float, complex, or even Boolean. And we can also mention the history if at all there was any changes made into the FITS data. Now, there are two kinds of keywords. One are mandatory reserved and the rest are optional. There are mandatory, for example, simple bitpix n access because it gives us the number of data access, and the others listed here. Um, these are fixed. When I mean what I mean by fixed is this is the way the keywords ought to be written into the FITS file. Um, for the optional, which we can see again in this image, our comment, the object, of course, not CR, well, I mean, somehow this got descaled. But for example, the object, the name of the object that was observed. So these things are optional, and FITS file can be constructed even without mentioning these keywords. Now, coming to the data unit, this is where our data lies. We can divide the types of data into three: ASCII tables, binary, and also image file. So I am showing an example over here. On the right, we have a binary table actually. We have the wavelength and flux. Of course, we take them and we plot them, these data, and we have the spectrum as seen on the left. Binary tables have an advantage over ASCII that they are faster to read. For the image extension, so in this case, what happens is if we open the table, each element in the data array represents a pixel, and I have purposely highlighted this one and the the one with the yellow 1040.91. If we see on the left, it actually shows us that it corresponds to the physical pixel 8110, and on the graph the coordinates are in pixels, and we can see that this refers to the bright point and it's in counts. And if we go along the same column, but to higher row numbers, for example, we will see that the values start decreasing. So this is what the FITS file, the image file, is holding. So to recapitulate, FITS is composed of header data units. It has a primary header data unit and extension. The primary header data unit is always present in a FITS file. Now, each header data unit, be it primary or extension, has header and a data unit. The header is in ASCII. The data can be in binary, ASCII tables, or image. However, in case of primary data, only the image extension can be present as far as my studies and what I have learned so far. Now, I would show you some examples in Python notebook. Um, we'll be dealing with basic commands like open to open a FITS file, close to close it, information to get the information about what is inside the FITS file, the number of HDUs, then to access the header, then access the header with a keyword of our choice. Data will enable us to peek into the data corresponding to a header data unit. Then image HDU, the second line corresponds to when we are actually writing um, the FITS file. Okay, so um, yeah, I'm using Astropy, and I call a file stored in a location. It is done by the command dot open. This opens the FIT file, FITS file, and the dot info the info command gives us the information, and this fits contains two header data units: the primary, the type as it shows here, and it's a table HDU for the second header data unit. We have 262 cards. That means 262 entries of the keywords, which is clear from here because what I've done is I've taken the header length and printed it. So it shows me that it's 262. And it tells us the format is in float 32. Now, what I've done is I read the header data unit headers to have information about what's in there. So for the primary, header contains this thing that we can see, and it shows us that the origin is STSCI, STS DAS, and when it was created, uh, and the date on which the fits was created. So just to see, that this is what we can have a lot of information, the instruments used, so on and so forth, the telescope used. Um, Coming to the table header, the second header data unit, it gives us also the information of the t-type, basically of the data that is stored there. Now, if we do not really know what the keywords are pertaining to a header um, of an HDU, we could use this command, keys, and it lists all the keywords that are used for an HDU. So I have, for this example, I'm focusing on the primary header data unit, and we can see that there is the simple, the essential ones, and also the non-mandatory ones like the comment, the detector, the telescope that has been used, so on and so forth. Now, how do we access the information in the header? One of the ways is to actually use the keyword itself. For example, we want to know which telescope was used in order to obtain the data. We use header, and the keyword for finding telescope is telescope without an e. Otherwise, it exceeds the 8 characters. So it gives us HST. Same for the instrument. It gives us WFP C2, and what was the equinox? It was 2000. So this enables us to really play with the data and have detailed information. Not only this, but also uh, the keyword T unit gives us information about what are the units in which the data is stored, and I will show you in the further examples. Now, having obtained the information about the header, how do we read? So, how do we read the data? Uh, so it's a very simple command. It's just data, and the corresponding header data unit. So if I type primary image, which is the first, the first HDU header data unit and data, it will print. It will give me the data corresponding to that. And same holds true for table image. When I'm writing table image dot data 0, that gives me the the information from the first row. And of course, then we know how to manipulate these. If we want only the first element, I just put a 0 over there again to take the first element, and we could do that. And same holds true for the primary. And these are the pixel values. For the over here, the 0 corresponds to the first image, because there are 4 images in this, as we can see here. So 200 by 200 into 4. So 4 images. So this, I'm showing you the example for the first image. Um, okay. It is also possible actually to access any of the rows, um, if we want to look into it. If in case there are dead pixels or something of that sort, which I mean that goes to the more advanced part. Then what I've done is I have plotted all the 4 images, and this is done by the imshow command, and this gives us the 4 images over there. And of course, this is now in the physical units, that is the pixel coordinates. And having image this in this way enables us to manipulate it for example, to calculate photometric data, or in case of galaxy, we fit it with some profiles, brightness profiles, to extract some things of our interest. Now, about closing the FITS file, there is a way to close it manually, and there is also a way by using the open as a context manager, which I have shown here. So both of these. Now, to look into a bin table example, um, I select another FITS file, and in this case, we have a primary header data unit, but the extension is a bin table, and I read the bin table header, and it tells me that it's a template, gives me information about the file, um, and also to look into the header of the extension. One thing to notice here is there's if there are extension datas, we have the keyword called extension, and it gives also the information. What kind of extension is it? Is it a bin table, or is it ASCII, or is it an image? And it also gives us the information about what are the units, as I was saying. T unit 1 so corresponds to the unit of wavelength, and T unit 2. Then I take the data, and I plot it. So we get the spectrum. So this is how we can extract a spectrum from a binary extension, and then I close it. Also, there is a way to store the spectrum as an image, um, which is not actually an image, but a one-dimensional array. In that case, what happens is that we need the keywords called CDELT and CRVAL. And these are very important. And then the n-axis. So we need to have the number of pixels, which will correspond to the wavelength points. We need to know the starting value of the wavelength in angstrom, and then the steps. And what happens is if we write a code which can then reconstruct the spectrum by constructing the wavelength given by this form, we have the spectrum. And in this example I just showed, that I take the data, and just take the flux, and then the wavelength is calculated using this formula, and then I plotted. And in this case, what I have done is I haven't even manually looked into the units. I've just used the header, and it gives me the appropriate unit, and then I close. So this was about reading FITS file, very basic. And of course, after extracting the data, we can do whatever we would like to do with it. Now, to create a FITS file, what I'm doing now is I'm creating a FITS file with multiple extension, just so that we can um, start with the most complex case, and then go on to the easier ones. So what I have done is I create a header for the primary. I create a header for the image, and a header for a table, a binary table. So in this case, I'm planning to create a HDU, which is primary, and then the secondary is image, and the tertiary is a binary table. So I can give any comments that I like. So I've written this is primary header data unit. I create a data. Now I create the primary header data unit, which will of course be composed of the data and the corresponding header. In the same way, and this is done by primary HDU, in the bracket we give the data and the header, which I have created here. The same holds true for image. I give a image comment, uh, just to show you that we can give any keyword of our choice. Then I create a data, and then with the help of image HDU, that is the image header data unit, with the corresponding header data and the data itself, I make that header data unit. And for the bin table, what I've done is I create different columns, I compile them together with the dot from columns, and I use the header data for the table over here. Now, having done that, what I need to do is the primary header data unit was created, the image header data was created, as well as the table header data unit was created. Now I compile them together and I write it to a FITS file. And that is done by the HDU list command. So we have the primary HDU, image HDU, which holds also the headers, and as well as the table, which also has the header. And then I write it. I have named it multiext.fits uh, just to show. And then I open that just to show you that it works. That we have the primary header data unit consisting of 7 keywords and 100 by 100, which is the data I have created the numpy array. And the comment that I had written comes in here. The extension, because it's an image file, comes here. And the comment comes in the comment section. The same holds true for the bin table. And it gives us that it's a binary table and the data forms as well as the comment. And then I finally close it. So the thing is that we could this I mean I have used any arbitrary data, but also for that data we could use flux and store spectra in multiple layers or multiple HDUs as images, for example. And that's what we do because I'm from the Galaxy group. So that's what we do, and it does increase the file size, but it's very very efficient and very easy to access because if there are certain parameters to vary, what we do is we change the parameters on each layer, or what I mean by layer is each header data unit, and then we have a complete cube of um, of, of spectrum for different parameters. Um, so in addition to that, if one needs to look and understand more on fits, I strongly recommend going through these websites. They are very useful, and especially the first one, because in the first one you have available codes to deal with fits file, and it's a very very easy to understand website along with very good examples, and it's very interactive. So finally, I come to the end, and the life of astronomers have been made easy because of fits. I mean, at least that's what seems to me. So thank you for your attention. If you have something to add, something to ask, or something to tell me, which will also enhance my knowledge, I'll be really grateful. Thanks for your attention.
Thank you for
Thank
your
you for your
nice presentation,
nice
Abhi.
presentation.
I'm
You're
getting.
welcome.
So I have a question slash comment. So I'm going to start by me. Sorry, everyone else, if you have any question. Um, so when we are dealing with image data and you load it with Astropy, the data is in a different orientation than you have it on a file, right? So the axes are inverted, isn't it? Or I'm
Yes, that's true. Yes.
okay. Okay.
But I mean, what I usually do is I transpose and then I write it.
Yes. Sorry. Okay. I was just wondering if that was the case or I was just misunderstanding something.
No, no, you are right, Andre. I should have mentioned that. Thank you for mentioning. Yeah, I do transpose and then I write it. That's true. Yes.
Okay. And just another question regarding your comment. So you say that when you try to use a keyword with more than 8 characters, there is a warning from Astropy, I would assume. But does it write the entire keyword to the file? Does it put an hierarchy card in there, or how does it handle in the actual file?
So what it does is it actually writes the characters completely. But on the left, you would have, I mean, on the keyword, it will say hierarch card, and then, I mean, or hierarch, and then it would write whatever you want to write there.
Okay.
Yeah. Meanwhile, when we are by the time we are talking, if there is some, maybe if I find an example, I can show you.
No, I know what are IR cards. I was just wondering how does Astropy deal when you give a... If you have to manually select or manually tell it that it's an IR card or if it does it automatically for you.
No, no, it does automatically. Yes, it does.
Okay, okay. Thank you. So, does anyone else have any question or comment to add?
I have a bit of a question if no one else has.
Sure, go ahead.
Okay, so I'm not the type of person that uses FITs for my work. I use other file formats like Adios and HDF5. So I was just wondering, so if you do know these file formats, if you can tell me some of the relative advantages or disadvantages of FITs versus these formats, like for example, in terms of performance, how does FIT compare, you know, features, etc.
What are the other formats that I should compare it with so that I have a relative idea what to focus on? Could you please tell me that?
For example, HDF5.
I have never worked with them, actually.
Okay, okay.
I think that you don't have much of a choice in what type of data file you use, since you are using data from instruments and you just use what they give you.
Yeah, well, in that
I,
case.
I think it will not be useful to just use uh, so load your fits data in memory and then write it to another file to then process it. I'm not
No,
in,
no, that is useless. You have a point. But I mean, I also work in a completely different thing. So in simulations, I write my own data.
yes, in that case.
So like, if I control all the pipeline, it's you know, I can just decide whatever file format I choose to use.
Yes.
Uh,
In that case, yeah, you're free to use whatever.
Well, I have to look into it again, but when I was reading the paper and the documents, of course, I cannot compare it with the other format that you have mentioned. But as far as the accuracy is concerned of the data stored of the floats, let's say it's very good. That's what the paper says. That's what the document says. So that's what I can think of. But since I do not know the other format, I have no basis of comparing. The advantages over that. One advantage would be that it can deal with binary very well. You can store binary very well in fits. But if the other does the same, then it's useless to compare, right? I mean, so yeah.
I mean, it depends a bit. So HDF5 normally people just use for parallel I/O and stuff like this. It's also very extensible in the sense that you can just put groups of data sets, or data sets can be whatever you want. They can be images, they can be arrays, they can be basically whatever you wish. They can be binary, and you can even put attributes. And to some extent, fits does remind me a little bit of that, right? So from what I understood, you have the header unit, which is basically attributes data, and then you can put different images or different data sets inside a single file, correct?
Yes.
You're absolutely right. Yeah, that's true.
And however, one of the downsides that you might have with fits, you talked about it, is that so they select the maximum. Let me think. So they select the maximum number of bytes that you can have in each header. Let's say it like that. And if you go over that amount, they add an equal amount on the bottom, and then zero pad it. So if you are using one more byte than the default size, you'll have 2 times the default size due to that 1 byte.
Ah,
I'm not sure, Andre, if I understand you. Could you please reframe it?
Sure. So when you store, so the fits format stores the data in blocks of I don't know how many bytes, but there is a default size for it.
Mm-hmm.
And your data unit is multiple blocks of that same default size put on top of one another. And so if you go a little bit over one block of the default size, they will add another block of default size, and then they fill it with zeros.
Okay, that could be the case, but I have to look into it.
No,
I'm not sure.
that is the case.
Oh, it is? Okay.
Yes, yes. And
Okay, okay.
even they do that for the data and for the header. So if you have 81 bytes on the header, they will just put 2 blocks of 80 bytes. And then from the second block, they only use 1 byte.
That can be annoying in terms of the header, because
Yes,
attribute data is extremely small, right?
you'll always use the same amount of data.
Yeah.
Which is a downside of the thing, yes.
By the way, I noticed that in the header unit you have several keywords. Are these keywords like just the ones that exist, or can you add?
No, you can add them.
Okay.
The
Okay.
default ones I think are the number of so the length in each axis of your data
Makes sense.
and the amount of bytes, I believe. So yes, exactly that ones. The ones that Abby has highlighted in this plot are the default ones, and I think that everything else is added by you. Isn't it the case, Abby? Or
Uh, yeah, more or less, but I'm not sure, Andre, if I have missed on some of the mandatory or the reserve, let's say, the reserve ones. But I have to look into it. Most likely these are the ones. I'm 90% sure these are the only ones which are fixed, and the rest are optional where you can,
yeah.
yeah.
Oh, and I think there is one extra reserved keyword which is the checksum of the file.
Makes sense, actually.
I'm not sure if it's if by default you have a checksum of the data, or if you have to add it manually if you want. But
Um, I think so. What you are saying is right. I think it has it.
It's a particularly wonderful way to immediately check if the data is corrupted or not. So
yes, that is useful. Yes. And for example, if you use the fits viewer file, the one that you are seeing here in this plot, you can change the fits file from it, and then you can recompute the checksum. So if you want to make any alteration,
yeah.
you can avoid corrupting the data, or having a data different from your checksum, from your previous checksum.
Well, that is already a nice little advantage over HDF5, because in HDF5, if it corrupts, and that's it. Bye.
I mean, you could also compute the checksum yourself.
True, but having it done automatically is a little nicer.
Yes.
All right, I think that's all my questions. Thank you for the answers. I don't know if someone else has any questions or comments to add.
I'll guess no, so I think we can end here this our last Programmers Club of the year. We will be back in January, and we will send an email later on telling the details as usual. So everyone have a nice Christmas and a Happy New Year.
Thank you so much, Andre. Wish you the same.
Thank you.
Happy holidays, everyone.